Hello everybody. Today's lecture focuses on another area in generative machine learning, which is autoencoders. And these, like the reinforcement learning methods described in our previous lecture, have been used quite a bit for creating new molecules. So just to recap why this is interesting, we'll go back to the example we used in last lecture, noting that chemical space is enormous with both large numbers of different kinds of structures and different kinds of functionalities available through molecules. And given this kind of basically infinite space of possible materials, you really want to come up with ways of sampling only a finite section of it that you think might have interesting materials for you. For example, you can say look at molecules with general substructures. Now, the challenge in doing this in molecules, to say being able to take a particular drug-like molecule and say just generate a bunch of them like it for me, is the complexity of how molecular structure and molecular properties are related. So to illustrate that, we'll consider a simple example of consider you're given a task to replace ethanol with a different solvent. Now, I could consider two molecules, say propanol and dimethyl ether, and naively I could say that dimethyl ether has the exact same composition as ethanol, so therefore I could assume it has similar properties, which is very wrong. In fact, we know from chemistry that the presence of functional groups like this alcohol group are really what drive functionality, especially for properties like solvation. So I'd rather pick this this one propanol molecule as a solvent instead of dimethyl ether. And this is to illustrate that you really need complicated rules to be able to take molecules and alter them in such ways that they give you a new material that might, say, miss some of the problems of the original one, but still maintain the good behavior that it already has. And you can imagine that this gets much more complicated with generating new molecules, because there are going to be very many complicated rules. And to me, that's really what motivates the search for machine learning, that we could, instead of having a human come up with the rules for how we generate these new materials, we could train a machine learning model that could say learn all of these rules automatically, and we could have an even better and faster way of creating new candidate molecules that we can, of course, run to generate as many molecules as we actually have the bandwidth to evaluate, rather than going back to, say, a space of 106 billion or 166 billion and searching through there. So there are many kinds of generative machine learning models. Reinforcement learning models fall under that class, and we discussed them at length in our last lecture. The one that we're going to talk about today is autoencoders, which, as we'll learn a generative model that takes some meaningful latent space of molecules, which here we denote Z, and use that to generate molecules that have similar structures. There are also GANs, which I can train a generator that takes random noise and uses that to create a molecule, which we can train this generator by building a so-called adversarial network, which qualifies whether this new generated molecule looks similar to a previous one, one that, say, has our targeted properties or not. And there are also another class of molecule generators that fall under the category of autoregression, where these molecules are created by removing parts of an original target molecule and training it to fill them in with the remaining groups that would give it the desired functionality. And all of these have been used, and they're described well by a textbook chapter by Schwalbe, Coda, and Rafa Gomez Barbarelli, which is actually part of a textbook that in retrospect I might have recommended for this course. I provide the link to it here in case you're interested in it. So as I mentioned, the point of this lecture is going to be to discuss autoencoders and how they're used for molecular design. But before we get into that in further detail, we're going to talk about the theory about what autoencoders are and how they work. And by the way, one of the reasons why we didn't do GANs today is we're going to talk about them in great detail in our image processing lectures next week. So we'll start off by explaining how autoencoders are useful by explaining a very simple kind of autoencoder in very general terms. Now the idea of when you train an autoencoder model is you're actually training two different models. I have an encoder that takes some data and compresses it to a latent space, something that captures the essence of that original data in a much kind of more compact representation. Then our second model we train is what goes through and takes that kind of distilled version of the original data and tries to reconstitute it to its original verbose form. And this is called a decoder. And we train these models by giving many samples of our original data and recording the pair of the encoder and decoder being able to reconstruct that data. And here I'm using a mean squared loss. If you can imagine that these data here are described by just simple numerical vectors. This gives us our best way of measuring whether they're exactly the same or not. And you may recognize this kind of technique from dimensionality reduction approaches in general if you've taken a machine learning course before. And one of the easiest of which is PCA, or say I can compress a two-dimensional space down to a lower dimensional one that captures, say, our rich 2D data as a single one-dimensional line, which I can pick such that it gives me a slope and intercept that I can place points along that line that are optimally close to the original data. And here I can take that original point, I can decode it back to a two-dimensional point in the original space, and if I, as I mentioned, pick my slope and intercept right, I can make them optimally close to the original data. And autoencoders are just a successor of this kind of compression technology where it can handle more complex data. PCA gives us a linear model to represent how my encoded state can be decoded back to the original space. Autoencoders give us arbitrarily complex nonlinear models. And the one thing that you may be wondering is, how do I ensure that this space that I compress to actually has meaning? Because as we motivated earlier, our goal in creating these kind of generative models are ways of being able to sample spaces. And there's yet no guarantee that, say, I make a small deviation from my original latent space and it's going to decode back into something that isn't just valid data but is also kind of meaningfully close in, say, having similar solvent properties if I've decoded to a model. Now the way that we do this is being able to look into variational methods. So before I step into those, I'll just give you an example here. You can imagine my autoencoder can learn, say, an arbitrarily complex model. Say if really that points A and C are closer together in terms of their properties than A and B, I can learn a encoding line that captures that desired ordering based on some metric in place to being forced with keeping them reflecting their original similarity in their original 2D space. Now, variational methods are one way about going about this, and what distinguishes them from a basic autoencoder is that instead of trying to learn a encoded space or a latent space directly, what I do is I map my original data to a distribution of possible points. And I regret having the spelling error so far in the middle of my lecture that I'm probably not going to go back and re-record it. But that distraction aside, again, what I've done first is take a neural network that takes my original data and encodes it to parameters of some kind of distribution. Then what I do to train the decoder is I take a sample from that distribution and I decode that back to the original model. And the way that I train this whole encoder and decoder now is I give my encoder a loss that is based on how much different these parameters are from a normal distribution. KL stands for Kilbeck-Lieber loss, which defines a difference between two different probability distributions. And I can train my autoencoder, the decoder part of my autoencoder, by taking my original distance metric that I defined before. Now this KL loss is really what gives us the magic of turning this space into something that's meaningful. Now one thing that it does is by the fact that we're training this model such that instead of giving a single point and ensuring that that decodes back to the original sample, like this point here mapping back to a triangle, I enforce learning a decoder function that's sensitive to noise, that say I can randomly displace from this point according to that distribution now I've learned, and that must also decode back to a triangle. And what this has the effect of is ensuring that points that are in nearby space decode to similar structures. So a slight perturbation in this latent space in which I've placed all of these shapes should decode back to something that, say, has three sides with roughly 60-degree angles. And so this red point is closer to satisfying that decoding than is a square or a circle. Now one other problem that we suit by using this KL loss, the first of which is we're using a distribution, so it ensures that nearby points decode to similar structures. But the fact that we're penalizing with that distribution matching term to ensure that these data map close to an original normal distribution means that instead of, say, finding a solution where I can achieve a good decoder by just making sure that any of those point clouds that describe a triangle or a circle are very far away from each other, so I never have to deal with the fact that nearby points have to ensure to decode into a circle instead of a triangle. I can force them to try to be close to, say, the same original distribution, which gives me a benefit of having a second penalty that not only trains my model to be able to decode similar points as similar structures, but prevents this kind of meaningless use of the entire space by just memorizing that similar groups are squares, and forces in that are together so that we can get nice properties of, say, being able to smoothly interpolate between different kinds of data, which will give us that ability to decode into things that have similar properties like rounded corners, but also keep on some of the properties of the original data. And the real trick with being able to do this in practice, and compared to all of those cartoons I've done before, is choosing a kind of neural network that describes the data that I'm giving to my encoder and the kind of data I want to receive as it being decoded. For example, if I'm considering text data, I might want to use an LSTM, which is a kind of neural network that works very well with sequence data, and this reflects the fact that the order in which words are presented is very important. Or I can use convolutional layers to represent images, and this is a great example of showing the power of variational autoencoders in general, that I can look at an autoencoder trained to recreate handwriting of digits, and you can see how it's been forced to learn a space that places similar digits nearby each other. See how 7s and 9s are closer to each other than 7s and 0s or 7s and 6s. And it also gives me the ability to smoothly interpolate between them because I've clustered those the way that each of these individual characters is grouped in that latent space to be nearby each other by forming that KL loss that pushes them to be part of the same distribution. So as I mentioned, the real secret sauce in developing an autoencoder for any kind of new application is coming up with a good encoder and decoder. And if you want some kind of creative and fun views on how you can do this with different kinds of data, check out this website, AI Weirdness. There are a lot of fun examples of how you can use generative models to, say, create pie recipes. It's fun. All right, so moving on back to science. So one of the ways that we can do this for actual molecular data is by, say, following a paper from 2018 by Rafa Gomez Bombarelli and coworkers, where they built an encoder that takes a molecule and represents it as a SMILE string, which a SMILE string is a text-based representation of a molecular structure. And given that it's text-based, we know that nearby characters are similar to each other. So I can generate them I can generate a encoding of what this string means by using convolutional layers that account for that kind of adjacency. That allows us to give a continuous representation of this original discrete molecule represented by a string of discrete characters. And one of the other tricks that they use to train this beyond using the variational losses, which as we discussed give that space good spatial properties, molecules are forced to be nearby each other and to be smooth. Slight perturbations should return similar molecules. They also use a supervised loss where they took the coordinates that were generated for a molecule and also trained them to predict some property, such that it ensures that the coordinates in this space are not just meaningful for recreating a molecule, but they're also meaningful for, say, being able to predict the band gap energy or the solvation properties of a molecule. To decode, they chose recurrent layers, which generate sequences of data, which are another valid choice for how we can create a set of strings. Convolutions could also be possible, but recurrent layers capture the fact that, say, if I have a open parentheses, I should probably have a close somewhere later in the future. And this relatively simple technique works rather well. They gave some really compelling examples in the paper where they showed that if I start with ibuprofen as a molecule, as I gradually step away, I change only a few molecules, but maintain some of the key features like this acid group for nearby molecules and the fact that it possesses an aromatic. But at the farther I move away, the more that breaks down. And you can also do things like interpolate between two molecules, and you can see it samples points along the path that gradually go from keeping a aromatic ring with some very long side chains on it, to adding a second one to be closer to the end group, to also having some that possess, say, aldehyde groups in smaller numbers than the original. Going into some of the technical details on how they did this, to create a version of the SMILE string that they can pass as a numerical object needed for neural networks. Neural networks require tensors of numbers, not letters. They use one-hot encoding, where I can say take O and represent that as a 0, carbon as a 1, and so on. And their output of the model, to be able to train it easily, they use a probabilistic version where, say, I can represent my probability of the first character being an O or a C or an equal sign, which allows me to recreate a loss function where I can compute the probability that my model will decode to the correct initial data X. and try to minimize the log probability of that happening. So I try to make it more probable for me to decode to the original X. So some of the bad things about this representation are the fact that, well, one, there's more than one possible decoding, and not all of them might be valid. Let's say if I decoded as a equal sign first, that would not be a valid smile string. The equal sign always has to come after a molecule because it's modifying, saying that this oxygen has a double bond. And you can end up finding that these methods are kind of limited in their applicability for the fact that as I decode only a vanishingly small fraction, here these authors found less than 1%, decode to a correct molecule. And not just one that, say, has a correct syntax, but also has chemical reason. Like here, I have an oxygen with 3 bonds. It's bonded to a carbon with a single bond and bonded to an oxygen with a double. That's chemically invalid. Now, consequently, a very active area of research moving into the future from this original paper in 2018 has been to create methods that ensure that I give better validity of our outputs. I say generate a valid molecule more often. And there are a variety of ways to do this. The first, which was demonstrated by Kusner in 2017, is to use grammar to describe a molecule. So what they do is they first start out by defining a grammar for smile string, and this is a technique that you might be familiar with if you're learned about compilers or programming languages, where I can take a molecule and I can break it apart into a big tree that defines how it's described. It starts off with a chain that has 2 branched atoms, which eventually break down into their eventual types. Now I can take this tree, I can branch it out as a set of rules, which I can then decode as a one-hot vector in a very similar way till I use that smile string. Say vector 1 could be the rule that corresponds to a chain. And I can take this long vector of individual rules encoded as numbers, and I can use convolutional encoders to encode that to a latent space that describes similar molecules. And then Kusner et al. Also demonstrated a clever way of taking this point, decoding it to some probabilities of observing a different rule in a big sequence, which through some clever algorithms you can eventually decode back into a molecule. And then they can train the whole system's ability to go from encoding a molecule back to its original self and be able to have a meaningful latent space of molecules that, say, order benzene by the similarity of its changes. There are also graph-based metrics that completely eschew having to deal with a smile string to begin with, where, as demonstrated by Jin and others in 2019, I can learn an encoder that uses message passing networks, which you might be familiar with from our homework, and our earlier lectures on deep learning for molecules, that take a graph and learn an encoding for it. And then the authors came up with a rather clever decoding function that can show you how I can take this encoding of a graph and decode it back into its original form, and even take a description of the atom types or the functional groups and figure out the best way for them to actually map back to the original atoms. So this shows a variety of ways for being able to encode molecules as meaningful subspaces and then decoding them back into the original molecule. But there's one dark side of these that I haven't mentioned, is that depending on what you train your molecule encoder on, you can get structures that are not likely to be synthesizable. For instance, this is a paper from Gao and Coley in 2020 where they showed that if I trained an autoencoder on GDB molecules, which are procedurally generated, there's no bias to this data set for being more likely to include molecules that have been observed experimentally. The molecules that one generates with an autoencoder are on average akin to their original distribution of data, not synthesizable, but rather if I say use a data set that includes only molecules that have been observed experimentally, I can get molecules that are much more likely to be synthesizable as I pick random points in that latent space and decode them back to an original structure. And this synthesizability metric is in itself something that's still under active research. Something with a high synthesizability score is actually still not guaranteed to be accessible experimentally. So with that asterisk, that wraps up our lecture for today. The three things I want you to be able to take home is variational autoencoders give us an ability to take an existing molecule, make small changes to it by, say, taking this molecule and coding it as a numbers in a coordinate system. Then I can make slight changes to them and decode it back to molecules that should have similar functionalities. And the way that I do that is by using variational autoencoders, which enforce me to learn that coordinate space in a way that similar structures are grouped together closely in molecular space, or in that latent space. And if I'm clever about how I design the way that I encode a molecule to that latent space and then decode it back, I can make better variational autoencoders that, say, learn more meaningful spaces, or at least decode to molecules that are more likely to be synthesizable.